Alright, been a while since I made a video, and now I'm trying to play some catch up, get all these videos made for you guys. So here is going back to postulates and paragraph proofs from the time that I was out. So here's our warm-up. We need to determine whether the stated conclusion is valid based on the given information. If not, choose invalid. So given that angle A and angle B are supplementary, our conclusion is that the sum of the two angles is 180. That is definitely valid. The supplementary means that two angles add together to be 180, and that's our conclusion. So this is valid. The second one, how many non-collinear points define a plane? Remember, we have to have 3 non-collinear points forming some sort of triangle to have a plane be defined. So the answer is 3. The notes today are going to be very short. Just getting through all the theorems would take a while, but since this is a video, you can pause and look at those as we go through. I will explain them quickly, and then we'll get through them quicker for this video. So our new vocab we're going to cover today: postulate, axiom, proof, theorem, deductive argument, paragraph proof, informal proof. So first thing here, these are all the postulates that go along with points, lines, and planes only. And so here, first one, 2.1. So we will refer to them as their number here, just so that we have easy reference. But for your sake, knowing what they say definitely is important. So 2.1 says through any 2 points there's exactly one line. So we have any 2 points given to us. We know that between those 2 points, or going through those 2 points, there's only one line that can do that, not multiple actual lines. 2.2 says that through any 3 non-collinear points, remember non-collinear from our warm-up here, and 3 non-collinear specifically, there's exactly one plane, so we can't have more than one plane having the exact same 3 points in them, unless they are collinear, in which case then it changes things. Then you have infinitely many when they're all on the same line. A plane contains at least 2 points, so that's a play off of 2.1. They're very similar. 2.1 says there's only one line that goes through any 2 points, whereas 2.3 says that a line has at least 2 points. You can have more than that on one line, but there's only still one line through any of those 2 points. 2.4, just like 2.3, plays with 2.1. 2.4 works with 2.2. A plane contains at least 3 non-collinear points. So obviously you can have more points on a plane than just 3, but it takes 3 to make a plane. And then 2.5 is only one different than these 5, within these 5 here. And it's that if 2 points lie in a plane, then the entire line containing those points lies in that plane. It's the only one that references all 3 things: points, lines, and planes. So if we have any questions throughout our practice problems that have all 3 things, we know that we're referencing postulate 2.5. There's 2 more here. These ones are the intersections of lines and planes. So first off, when we have 2 lines intersect, their intersection is exactly 1 point. And then we have 2.7 says if 2 planes intersect, then their intersection is a line. So here we have some pictures given to you, but lines intersect to a point, planes intersect to a line. Lines and planes, when they intersect, also intersect to a point as well, unless that line lies entirely in the plane, in which case then the entire line is your intersection, and the intersection between the line and the plane is the line. Here's our first example. We have a couple of buildings. So since we know they're separate buildings, we know we're talking about some different planes. Points F and G lie in plane Q. Pardon me. And on line M. Line M lies entirely in plane Q. So if we look here, we have F and G on the line that's on the white building. It says that we can see plane Q is like on the shadowy part of that line, or that building. And it says line M lies entirely in that plane, so we have all three things, right? Plane, line, and 2 points, points F and G. So that means that this is talking about our postulate that talks about all three. That is postulate 2.5. B says points A and C determine a line. So remember, A and C are 2 points determining a line. That is 2.1, whereas, 2.3. So that's our answer. 2.1 says that there's exactly one line that goes through any 2 points. So they're a little bit different. Can get a little confusing when you're answering ones about these two. Next problem, using the same buildings. Plane P contains points E, B, and G. So a plane containing the 3 points is what 2.4 says. Sorry about that. That's what says. That's what 2.4 says. Oops. Sorry about that. Helps when I turn on my pen. 2.4 is our answer for this one because it's talking about containing those points. You can't have more than that. Or you can't have more than that, but containing 3 points, it has to contain at least 3. Doesn't say that it's formed by those 3 though. And then B says line A, B, and line BC intersect at point B. So we're talking about an intersection, so it's either 2.6 or 2.7. And we're talking about 2 lines intersecting at a point, so that means it's 2.6. Now our next problems are going to be a little bit different. They're actually going to say we need to determine if the following statement is always, sometimes, or never true. Really, just always or never. We're never going to have a sometimes, because it's either true or false in these situations. So, if plane T contains line EF and line EF contains point G, then plane T contains point G. Once again, we have plane, we've got a line, we've got points. So we're talking about all 3. That means we're talking about 2.5, and that means that this is always true. It's always true, and it's referencing 2.5. Here's our next one. Same concept. Always, sometimes, never true. Line GH contains 3 non-collinear points. Non-collinear, by definition, means that they are not in the same line. And so we're saying a line contains 3 points that aren't on the line. That doesn't make any sense. So this is never true. And of course our reasoning is that non-collinear, or the definition of non-collinear, tells us that we can't be on the same line then. Last one of these, plane A and plane B intersect in exactly 1 point. So plane A and plane B, 1 point. So this is talking about 2.7 with intersections of planes, and 2.7 says they intersect in exactly 1 line. So that means this is never true. You can't have 2 planes that intersect to form a point. It has to be a line. Okay, so now you have the midpoint theorem. If M is the midpoint of AB, then AM is congruent to MB. So the 2 sides are congruent. And I believe this is it for our notes. The next thing is our exit ticket. Oh, talking about the proof process. Forgot about this, sorry. I didn't write this down because there are no more problems to work. Just kind of going over this information. So the proof process is kind of like you're solving a word problem. So what I like to do when I do a word problem at least. And first I list out all the information I'm given. So that's what you're... That's what you do first. That's step 1. List out everything you're given. Step 2 is to state the thing you're proving, or for a word problem, what you're trying to solve. Step 3 and 4 are pretty much what you're doing, like it's the work, right? So you create a deductive argument, so using theorems, laws, postulates, algebraic properties, and definitions, whatever you have in your toolbox to prove something to be true. And then the last step is so all the work, right? Solving. And then the last bit is to state what you have proven. So x equals 3, or whatever you're doing, and then you just state it out. And we are not going to actually do this. I'm just going to step you through. So given AC intersects CD, we're going to write a paragraph proof to show that AC and D determine a plane. So we know they intersect, which means they're not parallel lines. So there's our given info. We write down what we're trying to prove. And there's our paragraph proof. AC and CD must intersect at C, because if two lines intersect, then their intersection is exactly 1 point. Point A is on AC, and point D is on CD. Points A, C, and D are not collinear, therefore ACD is a plane as it contains 3 points not on the same line, or 3 non-collinear points. So there we go. We proved it. So now, ignore that, because we are way done with that quiz. And here's your exit ticket. Determine whether the statement is always, sometimes, or never true. Point N lies in plane X, and point R lies on plane Z. And you can draw only one line that contains both points N and R. So that always, sometimes, or never true.